Hello, it's Keith here, and this is lesson 7 of the simple series of my assembly programming tutorials. In this series, we create a single ASM file that does a simple task on all of the machines in my tutorials. This week, we're going to be looking at the Camputers Lynx, and we're going to learn how to create simple bitmap graphics on the screen. First, we're going to create an 8x8 smiley face, so a very simple tile kind of graphic, and then we're going to create the larger Chibico character that I use in all of my tutorials. So we're going to essentially learn how to do basic graphics, so if you're going to try and write your own game, this should help you out. Okay, well, let's have a look at our code then. Let's get straight into it. So this is our first tutorial here. This is going to create an 8x8 graphic on the screen, so let's just fire it up and see it working here. So that's what we've got here, this smiley face. Now, the Camputers Lynx screen is an 8-color screen. It uses effectively 1 bit per color channel, red, green and blue, so that gives a total of 8 colors, and the colors were very bright obviously, so bright red, bright green, bright blue, bright cyan, bright yellow, bright magenta and white and black of course. So that's the color palette we've got, and that's how it works. Now the way that it gets data to the screen is quite complex, because you can see this example is pretty large. But when it comes to the smiley face here, effectively we've got 8 lines of our character, and we've got 1 byte for the blue part, 1 byte for the red part and 1 byte for the green part. You can see we use no green in our character, but we use red for the smiley face here. So if we swap these 2 bits around, we could easily make the smile and the eyes green instead of red, and the blue column here, if we inverted all the bits, then the face would become black and the border to the face would become blue. So very straightforward data format, but getting it into the system is a little bit tricky. Now, if you're really interested in the Camputers Lynx but you know nothing about it, please see the other tutorial as well that I did on the bitmap graphics of the Camputers Lynx. I went into quite a lot of detail in that episode about how the actual memory banking works, because it's the memory banking that's the tricky thing. You see, the graphics memory is paged in and out of the system memory so that we can access the red and the blue channels simultaneously within memory, and also the green channel. You can't do both at the same time because they page into the same bank. Now the problem is, that's pretty straightforward really, but the problem is that the Camputers Lynx doesn't actually decode all of the bits of the address bus. The long and the short of it is that we can't write to our normal memory, our program code memory, while the screen pages are banked in. And this also means we can't use the stack during those times, because the stack is just normal memory. So we're going to have to work around that, and it's a bit of a pain, but it's perfectly doable. But we'll go through it in stages, and hopefully we'll make it pretty straightforward. But I'm not going to go into like huge amounts of detail about how the banking works. I'm going to show you the code that will work, but as I say, if you want to understand why the code that we're using today works and the full technicalities of it, then you're going to have to look at that other tutorial or go into the documentation there. Okay, so the first thing we're doing here is we're starting our program at hexadecimal 6500 here. Then we're going to turn off the sound. Now when we load our program in our emulator, we'll be making a loud clicking noise, and that's not very good, so we turn off our sound to stop that. Now the code that we're running today, if you've seen my Hello World example on the Camputers Lynx, I showed you how to actually get the program running on a Camputers Lynx there. So if you need to know how to do that, then please look at that. But you can run this example from my tutorial series, the download file for that. So that's the way you can get things started. So we're going to need to calculate the screen position, and we're going to need to have that in DE, effectively, the destination for our data on the screen. So we call this function getScreenPos. We're passing in an X and a Y position here, and they are in bytes. The X position is in bytes, the Y position is in lines, and getScreenPos is right down here. Now, the width of the screen is 32 bytes wide. Now, there's 3 bytes per pixel, but they're in different memory addresses, so we're kind of thinking of each color channel independently. So if we imagine the screen is black and white, it would be 32 bytes wide. And so when we want to calculate the memory position, we multiply the Y line by the width, 32, and then we add the X position, and then we add that to the screen's base address memory, and that gives us the memory address we want to write to actually get our pixels onto the screen. So the way we do a multiplication by a simple number like 32 is with bit shifting. So what we're doing here is we're loading in the Y position, which was in C, into H. We're using H as the top bit of a 16-bit pair and the accumulator as the low bit, and then we're just shifting 1 bit out of the top byte here, and we're shifting it into the low byte, and that will effectively give it, that low bit, the value of 128, We then we shift it to the right again, effectively giving it the value 64, and then one more time, and now the lowest bit has the value of 32. We've effectively multiplied the Y position by 32 with just a few bit shifting commands. That's all it takes, and that's the fastest way you can do it, to my knowledge, on an 8-bit machine. So that's what we do for our multiplication there. And then we're adding the X position here. And then finally, all we're doing is adding the screen base. Now the screen base is A000, but we're just adding A0 to the top byte and just leaving the bottom byte alone, because of course adding zeros make no sense. Now this function is using H, but we actually need it in DE, so we're just swapping them over here. We then load in the address of our test bitmap here. And then we need a counter for the number of lines. And we're going to use IXL, which is one of the rarer registers. You know, it's not one of the official, I think originally the official documentation didn't say you could use that, but you can, so we are doing. So we're using it as a general purpose register here. And the reason we're doing that is we need, really, because we can't use that stack, we're using all of the other registers, and we're also using shadow registers, which is something I really try and avoid. But as I say, in this case, we really need them, so that's what we're going to do. So that's our line count, and then what we're doing is we're flipping into the shadow registers. Now I've covered flush shadow registers before, but if you're relatively new to all this, I'll explain it. The Z80 has some shadow registers. It has AF, which is a backup copy. It's a spare accumulator and flag register, and the way it would swap them is it would swap the normal one to the shadow one, or vice versa. Technically speaking, it actually relabels them within itself. It doesn't swap the data at all. It just swaps the names within its own hardware. But anyway, so you can swap AF and A with a special command, but this command is EXX. This doesn't use that shadow AF. It uses the other three. So B, C, D, E, and HL will be swapped over for an alternate shadow set of B, C, D, E, and HL. And they're usually called BC apostrophe, but you'll never see that in code. All you'll see is this. And after this point, B, C, D, E, and HL will be different registers. But when we swap them back, they're back to their original values. Now, this does not affect IX, and it does not affect IY, and it doesn't affect the accumulator. We would have to do EX AF, AF apostrophe. That's the command to swap the accumulator, but we don't do that. There doesn't tend to be too many cases where that's particularly beneficial, because it doesn't save a lot of time, and if you were just using one register, you almost might as well push and pop. Okay, so what we're doing here is we're going to use the shadow registers for the commands to do the page banking. As I say, we can't use the stack. We've got enough registers for the data writing, but the page banking, we need too many other registers at the same time. So we're going to be page banking with those shadow registers. And what we're doing is we're loading BC with FF, and that's because we need to write the bank option to that address, and it's the easiest way to do it. So rather than corrupting BC, which we're using for other purposes around the place, we're using these shadow registers here. So we're preparing that for later. We're then loading DE, our destination address, into IY, because we're going to want a backup of that for when we're moving down to the next line of the sprite. Now what we do is we send two commands here, and these together will actually page in the red and blue component and make it writable. So we have to write 03 to that FFFF port here, and that will turn on the banks, and then we need to write hexadecimal 28 to port 80. Now this is effectively anything ending in 80, so even that we don't have to use a pair of registers to set that, so that will work just fine. And then these two together now, the memory address range A000 to B FFF will be screen memory now. And as I say, do not use the stack at this point. You can have a play if you want, and you'll see weird glitching and crashes, and just don't do it. So we're in no stack mode now, and what we're doing is we're using the LDI command here. This will copy a single byte from HL to DE, and it will mess with BC, but that doesn't matter in this case. We're not using BC in this case, because remember, the shadow BC is actually not paged in at the moment. The shadow BC will be available here, but as soon as this second EXX command goes, the regular BC is now present. So that's why we're using these shadow registers here. So we've now copied the byte, but unfortunately the LDI command affects DE. So DE is our destination. We need to move it back one to the left because we want to write to the same position again. Now these paging commands here will load in the red and blue memory here. So the blue component is at A000 onwards. The red component is at C000 onwards. So all we need to do is effectively add hexadecimal 2000 here. And what we do to do that is we just set bit 6 of D and reset bit 5, and that will actually convert the address, and now we're in the correct position to write the second byte. And that's exactly what we do. We do another LDI command, and that will copy the red byte, and that's why we're in this order here. We've got the blue byte followed by the red byte followed by the green byte. So we've just done the red byte there. Now we need to do another page. So what we do here is this time we write 05 to that quadruple F port and 24 to the hexadecimal 80 port, and that will page in the green component. And there's actually a second green component, so you could like page flip between two greens, but there's no red and spare red and blue, so it doesn't make a lot of sense, but that's what we got. Now the green component that we want to write to is at the same address as the red component, not the blue component. There is an alternate green there, but we're not using that. So we just write another byte without changing our D register again, and then we have now set that final one here. Now we want to move down a line. So each line's 32 bytes. So what we want to do is we want to add 32 to this copy we backed up here and then set it to the new DE. And that's exactly what we do here. Hexadecimal 20 is 32. We just add it, and then we update DE with the new IY value. We decrease IX, which was our line counter, and we just repeat. Now, at this point, we've finished. So we turn off the page banking here, which was what this caused. This is the mess that caused. And at this point, everything's back to normal. So you can use your stack just as every other day. So that's back to normal. And then all I've done here is just halt the processor. So that's the example there. Now, with a few little tweaks, we can make this into a much more advanced example. So this time what we're doing is we're resetting B here to 0. We are now doing a width counter. Our sprite that we're going to use here is 48 by 48. That's 6 bytes wide. So that's why we've got a 6 here as our width. And we've got our B to 0. And then what we're doing here is we're loading our width into C here. And this time we're using LDIR. Now LDIR will copy multiple bytes. It will copy BC bytes from HL to DE, which is exactly what we want. So this isn't effectively filling an entire line for us, but it does mess up DE, and we need to get DE back to the way it was. And we do that just here by loading from that backup back into DE each time. But apart from that, this code's all essentially the same. Not much change at all. And let's see it in action here. So I went to town a little bit, and I gave us a nice colourful chibico here. So we've got the yellow of the necklace here, and we've got a green kind of foot here. And yeah, we've got a bit more colour in there than usual. So the Camputers Lynx, the graphics screen's a bit tricky. It uses up a huge percentage of the memory, but you know, for the old 8-bits, it's quite a nice colour scheme really. I do quite like the very bright colour scheme, and it's quite refreshing after seeing the 4-colour systems. To have those extra 4 colours all the time is something of a change. So anyway, there we go. You can see we can quite easily get a sprite on here. Now, if you want to create your own sprites, I would like to draw your attention to my AccuSprite editor, which is what I created today's sprite in. If we go to Z80 here, and we've got Camputers Lynx and Save Raw Bitmap, this will export the bitmap into the format for today's example. Now, if you're using different code, if you were transferring the byte data in a different order, then you don't need to do things differently. But as I say, if you want to make your own code with today's example and you need to convert graphics, my AccuSprite editor will do it. You've just got to make sure you have the colors in the right order up here. Anyway, I hope this has been some interest to you. We're going to come back to the Camputers Lynx later on, so please follow on for that. And also, I've got many more tutorials on the Camputers Lynx already, so please check out my YouTube channel or my website and just see that. Anyway, I hope you found this interesting. Thanks for watching today, and goodbye. If you enjoyed today's video, please check out my new YouTube channel known as Chibi Ackerman's Live. This is going to be a live streaming channel, and it's going to be some more casual content. It will be me streaming some of my programming sessions, me playing games and chatting along. I'm going to try and really do a lot of technical content in there, try and explain things as I'm playing games, talking about the hardware or while I'm programming. And also I'm going to try and interact with the chat a lot. So if you really enjoyed today's lesson, then maybe you want more content and that will give it you. Equally, if you didn't enjoy today's lesson, if it was too hard for you, if you found it confusing, and you want something a bit lighter hearted, then it might be interesting to you as well. Though I guess you've probably already clicked off if you didn't enjoy it, because 95% of my viewers give up after about 2 minutes. But either way, thanks for watching and goodbye.